Today we shall discuss some problems. Okay. One is called the firing squad synchronization problem. What is this? I will read it out. This is called firing squad synchronization problem. Consider a finite one-dimensional array of finite state machines, all of which are alike except the ones at the end. The machines are called soldiers, and the one of the end machine is called the general. The machines are synchronous, and the state of each machine at time t plus 1 depends on the state of itself and its two neighbors at time t. The problem is to specify the states and the transitions of the soldiers in such a way that the general can cause them to go into a particular terminal state, firing state, exactly at the same time. At the beginning, all the soldiers are assumed to be in a single state, the quiescent state. When the general undergoes the transition into the state labeled fire and ready, he does not take any initiative afterwards, and the rest is up to the soldiers. The signal can propagate down the line no faster than one soldier unit of time, and the problem is how to get all the coordinated and in rhythm. Actually, this is called a cellular automata. Cellular automata. Somewhat like a finite state machine, you have one dimensional tape. I mean, this, it is divided into cells. Each cell is in a particular state, and the next instance, depending upon its states, the state of its left neighbor and the right neighbor, this will go to a state P. Suppose this is in state R and S, the mapping will be delta of RQ S is equal to P. So, depending on its state and the state of the left neighbor and the state of the right neighbor, this will change from Q to P. This is called a cellular automaton, because you know that for this cell there is no left neighbor. You can assume something like this, and the move of this will be always in that particular state. So, the move of this depends only on it and the right neighbor. Similarly, the move of this depends only on the left neighbor and itself, does not depend on the right neighbor. The last two cells are slightly different. Now, all of them, these are all called soldiers, and they are in a particular state called the quiescent state. That Q naught is called a quiescent state. And general goes to a different state. The leftmost person is the general. So, he propagates some signal to the soldiers, right? And when he propagates that signal, the next, depending upon the Q1, Q naught and Q1, this may go to say Q1, and depending upon Q1, Q naught and Q naught, this may go to Q1 in the next instance, and so on. All these cells change state simultaneously. The next instance, everybody will change the state. This is time t is equal to 0. At time t is equal to 1, everybody will change the state. So, next instance, they will be say P1, P2, Pn. The state of any particular cell was changed because of this left neighbor and right neighbor. Depending upon its own state, left neighbor, right neighbor, it changes state. So, all of them change state simultaneously. Yes.
Is the transition sequential or in parallel?
The transition is parallel.
So, for the second cell, is it delta of Q naught, Q naught, Q naught, or delta of, let us say, P2, Q naught, Q naught?
No. I will, instead of Q naught, initially let me take it like this, Q1, Q2, Qn, n cells are in these states. Next instance Q1 will change to P1 depending on Q1 and Q2, because this will not consider the left neighbor. Then this is t is equal to 0, t is equal to 1, Q2 will change to P2 depending upon Q2, Q1, Q3. Then Q3 will change state depending upon Q2, Q4 and Q3, it will go to P3. So, this is the set of states at t is equal to 1. The next instance it will again change like that. Okay. All of them change state synchronously, parallelly, right. Now, what I meant by saying this is, initially all of them are in Q naught. So, if a cell is in Q naught, the left neighbor is in Q naught, right neighbor is in Q naught, this is called the quiescent state, it will go to Q naught only, right. So, next instance what happens is, all of them will go to Q naught, but this may go to say some Q1 or Q2, whatever it is, you have to write the mappings, and this will also change, go to some state Q2 also. The next instance this t is equal to 2, this can go to Q1. So, the mapping will be delta of Q1, Q0 is equal to Q1, it will be like that. Like that this Q1 state propagates like this. It can pass some signals like that. So, at time t is equal to 2 there will be some sequence, t is equal to 3 there will be some sequence and so on. So, all of them should go to a firing state at a particular instance, and none of them should go to that state earlier than that. None of the soldiers should go to the firing state earlier than that. All the soldiers generally, everybody will go to the firing state simultaneously. The order is given and they after some time they have to fire simultaneously. This is called firing squad synchronization problem. This was stated I think in 1957 by Myhill, and lot of during the 60s and the 50s there was some discussion on that. Now, the mapping or the delta mapping you have to write for that, and that should not really depend on this n, this is the number of cells. The delta mapping which you are going to write should not depend on n. And another thing is, all these are similar. If you have delta mapping for this cell, you have the same delta mapping for this cell, you have the same delta mapping for this cell. Only the end cells, this one will not depend on the left neighbor and this one will not depend on the right neighbor, right. So, rest of it every cell has the, so if I have 20 soldiers or if I have 30 soldiers, the mapping I should write is the same, it should not vary, right. So, write down such a mapping in such a way that all of them reach the firing state at the same time, but none of them reach the firing state earlier than that. Okay. So, actually the mapping will be a lengthy process to write. The idea, the solution for this is like this. Initially this general, he sends one signal like this, one signal like this, this is one signal, he is sending another signal which is 3 times slower, this is 3 times faster than this. So, this can be propagate one cell at a time, this propagates one cell in 3 units of time, this is 3 times slower than this, and this signal when it reaches the last person it is reflected. So, you have to that reflections passing signal you have to take care in the states. So, they will meet here. When they meet, it is the middle point. It will be 2 cells or 1 cell depending upon whether you are having even number of soldiers or odd number of soldiers and so on. So, afterwards from this actually you can write 11, 12 or something like that, thirds. If you carefully write, you can write down the mapping within that. The mappings do not depend on the n, the number of soldiers, but the time at which they fire depends on n. When do they go to the firing state? This the last is the firing state, all of them go to the firing state, that depends on n. So, from here in the middle point, one signal is sent here, another signal is sent which is 3 times lower. This signal when it reaches here gets reflected, and when they meet it will be the midpoint of this portion. This is marked, this some signal is sent like this, so that this portion is marked, and in this direction also one signal is sent like this and another signal is sent which is 3 times lower. When this reaches the right end, it gets reflected and reaches here. So, this middle portion is marked, and now these 2 cells are marked, again they do the same thing. So, they send one signal here, one signal here, and there are 2 signals which are slower, 3 times slower like this, which is like this, which is like this, and so on. So, in the middle point they will meet. So, all the middle points are marked, then the next stage all the other middle points are marked and so on. Then all of them will go to some star state simultaneously, then the star state, when all of them are in star state, they will fire. So, you have to write down the mapping, I mean it is a sort of a lengthy process, sit and write down the mapping, but the idea is this. How much time it will take? To go to the firing state, the time t is equal to t0 you are starting. At what time you will reach the firing state? You can give many solutions. The solution is not a unique one, each one can give a different solution. It is not very difficult to give a solution which takes time 3n to 8n. You can give something 3n, 4n, in between 3n and 8n you can give. But the optimum time is 2n minus 2. It has been proved that you can do this in the optimum time 2n minus 2, and for that the number of state required for a cell in the delta mapping, it will be the order of 1000. So, it is a very difficult proof, but it can be done in 2n minus 2 moves, but something like 3n or 4n or 5n we can very easily give with say between 10 and 20 states. Okay. This was has been considered for a long time, and having discussed this, I will also mention what is meant by a cellular automata. This is called a cellular automata. You also have 2-dimensional cellular automata. You have cells, on each cell you have a finite state automaton, or this is a cell, this will change its state, each cell will be in a particular state, and this will change its state depending upon left neighbor, right neighbor, up neighbor, down neighbor, and its own. So, depending upon these 5 states, it will change state. Now, such a cellular automata was first defined by von Neumann. Von Neumann defined cellular automata first. He has a book written self-producing automata, self-reproducing automata. Then they talk about universal computation, universal construction, self reproduction, these things are talked about in cellular automata. Universal computation is like a universal Turing machine, it can compute any computable function. How can you do with a cellular automata? Universal construction is given some basic portion, non-blank portion here, you can construct the move of a Turing machine or something like that. I mean, I will just put it like you will be able to construct the encoding of a Turing machine or a cellular automata for that matter. Self reproduction is given something, it will make a copy of itself after some time and leave it to work by itself, that is called self reproduction. So, all these things were considered. They also talk about 8 neighbors, this is 4 neighbor, you can also have 8 neighbors and so on. Lot of work has been done on cellular automata, this is called one dimensional cellular automata. Lot of work has been done on this and still work is going on, and cellular automata have lot of application, VLSI design, VLSI test pattern generation and all that, it has got lot of application. Even in some physics and all it has applications, because many of the cellular automata papers they appear in Physica D and things like that. Another thing is called a generalized firing squad, generalized firing squad synchronization problem. What is this? This cell, number of cells, when you are doing, this is also allowed to grow. When you are allowed to grow, all of them change state, at the same time one cell can split into 2 or 3, and that such a thing can also happen. That is called generalized firing squad synchronization problem. This finds application in some modeling of biology. In fact, they show that this model is useful when they want to observe the pattern on a tortoise, on the shell of a tortoise. The things keep on changing, growing, and at a particular time the pattern on the shell will suddenly change. So, they all reach the firing state or something like that they say. There is also something called a French flag problem. You can say Indian flag also, because Indian flag also has 3 colors. So, whatever you start with, these cells you start in any stage, and finally it will divide, it may pass some signals, and finally it will divide into 3 portions, and say red, white, green, something like that. It will become equally, it will divide into 3 portions, and all of them will be in the same color. So, that sort of a thing is also possible. These are some, these are really useful in L systems named after Lindenmayer, which is useful in modeling plants and getting some beautiful pictures. So, the actual mappings you have to write down now. The second question is, consider the toy shown in figure 1. There are 3 levers x1, x2, x3, and the marble can be dropped in this place A or B. When it is dropped in this hole, it is considered as a 0 input. When it is dropped here, it is considered as a 1 input, and if it comes out of this hole, the output is taken as C, and if it comes out of this hole, the output is taken as D. Marble is dropped at A or B. Levers x1, x2 cause the marble to fall either to the left or to the right. Whenever a marble encounters a lever, it causes the lever to change state, so that the next marble to encounter the lever will take the opposite branch. Model this toy by a finite state automaton, denote the marble in A by 0 input and a marble in B by one input. A sequence of inputs is accepted if the last marble comes out at the position D. Describe the set accepted. Model the toy as a Mealy machine whose output is C and D. Okay. So, how will you model this? Again, writing the whole thing is a lengthy process. The idea is like this. The state of the machine can be specified by a 3 tuple like this or something like this. A state can be specified like this, denoting the position of the levers. This is say lever 1, we called it as x1, x2, x3, right. I will call them as x1's position, x3, x2, middle one is x3. So, I will call it as x1, x3. Either way you can change the order, does not matter. So, how many possible states can be? Each one can be this or that. So, 8 possible states will be there. There will be 8. Initial ID is initial position in which, suppose it starts in this initial position, this will be the initial state. Now, in this position you may get a marble through hole A or hole B. If you get a marble through A, what will be the direction it will take? It will fall like this and it will go here. So, output will be C and it will change the position of this, but these two will be unaffected. So, if you get a 0, the output will be C and you will go to the state, the first one will change to this, second and the third are unaffected, right. Now, if you get a 1 or if the marble falls through the B hole, what will happen? See, this is like this. So, the marble has to come like this and it will go like this. So, it will affect the second one and the third one, the first one will remain as it is and the output will be a C. So, like this you can model the whole thing as a Mealy machine or as a Mealy machine. Now, when I want to consider this as a input output device, this is okay. When I want to consider it as a accepting device, I have to also look into the output. So, actually the state should be taken as a 4 tuple. This will be CRD. The last output is C, you go to whatever it is, x1, x3, x2, x2, C. If the last output is C, if it is C, here you will go to this comma C. The last output is D, it will go to x1, x3, x2, D. So, when D is there, it will be a final state. The last output has to be a D condition. If you want to look at it as a input output device, a sequence of is accepted if the last marble comes out at D. So, now you have how many states? How many states you have? 16 states you have. And if you have D in the last component, that will be a final state. Okay. See, initially there will not be any output, first output will not be there, only when it comes through it will be output. So, initially one more initial state you can have, 16 plus 1, 17 you can have, does not matter. So, this is the way you model it, the details have to be worked out. Set you have to solve by the regular expression by solving. It is not a very, or you have to look at the pattern. The pattern will not be very easy to look at. The only way you can describe the set is by means of a regular expression, for which you have to write down the equation and solve. 13. Why?
After removing unreachable states.
Unreachable states can be removed. You have to work out the details. Unreachable states can be removed. If you remove them, there can be less number of states. But then you have to write down the equation for them and solve for the initial state, which will give you the regular expression. That regular expression will give you the set of strings accepted. Okay. So, it is a lengthy process, you have to do it. It is a method. So, going to the next problem, give deterministic or non-deterministic finite automaton for the following language. The set of all strings over the alphabet ABC that have the same value when evaluated from left to right and right to left by multiplying according to the following non-associative table. What is the table? This is the table, right. So, you give a finite state automaton which will accept strings which give you the same value when evaluated from left to right or right to left. This table is a non-associative table and a non-commutative table, right. So, I explained earlier what is meant by right evaluation and left evaluation. A1, A2, A3, AN. The left evaluation is this A1, A2, then this, then this and so on. That is, you first consider A1 star A2, then star A3, then star A4. This is the left evaluation. What will be the right evaluation? The right evaluation will be A minus 1 star AN will be calculated first, then AN minus 2, this, then AN minus 3 and so on until you get A1 star like this. It is not AN, see the usual mistake people do is consider AN star AN minus 1, AN minus 2, that is not correct. Given this problem, many make this mistake. This is not correct. Right evaluation means this, right. Now, what sort of strings will have the same value when evaluated from left to right or right to right? For example, take one string A, whether you evaluate A gives only A. So, whether you evaluate from left to right or right to left, it gives the same value. So, it has to be accepted. Now, suppose I have ABC, what will happen? Let me check. What is AB? AB is A, AC is C, left evaluation is this C. What will be the right evaluation? Let me check. Maybe it also BC. What is BC? B, and AB is A, right? AB is A. They are not the same. So, ABC should not be accepted. Okay. Any string which gives you the same value when evaluated from left to right should be accepted, other string should not be accepted. How will you describe this with a finite state automaton? You can have a DFSA as follows. The construction is like this. The DFSA will have 3 power 5 plus 1 state. How is that? What is 3 power 5? 241 plus 1, 242 states. 81 into 3, 243 plus 1, 244 states. 244 states it will have. How are the states defined? Initial state is there on Q naught, right. Apart from that, the states are denoted by 5 tuples. 1, 2, 3, 4, 5 tuples, right, and each one can be A, B or C. Each of the component can be A, B or C. So, first component can be A, B or C, second component can be A, B or C. So, that is why you get that 3 power 5. So, each state is denoted as a 5 tuple. Now, what does that 5 tuple mean? The meaning is like this: starting from the initial state, after reading x, you go to a state P1, P2, P3, P4, P5. And what it means is P1 is the left evaluation of, it will denote the left evaluation of the string x, and P2 will denote the right evaluation of that string, and P3 will denote the right evaluation of XAR, P4 will denote the right evaluation of XB, P5 will denote the right evaluation of XC. So, these 5 letters A, B, C, A, B or C, they will denote, if you reach this state from Q0 after reading a string x, means the first component denotes the left evaluation of x, second component denotes the right evaluation of x, third component denotes the right evaluation of XA, fourth component denotes the right evaluation of XB, fifth component denotes the right evaluation of XC. So, after that, how do you define the moves? So, if you have a 5 tuple like this, if you read A, you will go to another state, right, which is say S1, S2, S3, S4, S5. Now, what is S1? S1 is the left evaluation of XA. You know what is this? This is one of the ABC. So, from that and A, by looking into the table, you can fill this. You will be able to fill that this is the left evaluation of XA, right. Now, what is the second component S2? It is the right evaluation of XA, is not it? From here, after reading XA, you have reached this. So, second component should give you the right evaluation of XA. But what is the right evaluation of XA? It is P3. So, second component will be whatever value you have, that will be. Now, what about the third component? Third component is the right evaluation of XAA. But what is AA from the table? A. So, it is the right evaluation of just XA, right. So, S3 will also be P3, right. Now, what is S4? It is the right evaluation of XAB. It is the right evaluation of XAB. What is AB from the table? A. So, that is the right evaluation. Right evaluation means first you have to evaluate this. You know AB is A. So, it is the right evaluation of XA. Right evaluation of XA is again P3. So, this will be P3. What is the last one? It is the right evaluation of XAC What is AC? AC is C. So, it is the right evaluation of XC. What is the right evaluation of XC? That is P5. So, S5 will be P5. So, from one phi tuple, after reading A to another phi tuple you will go, and these phi tuples you can determine in this manner. Similarly, for example, if you take a B, let me take a B here, then you will go to a phi tuple R1, R2, R3, R4, R5. What is R1? That is the left evaluation of XB. You know the value of left evaluation of P1, multiply with B, you will get the left evaluation. What is this one? This is the right evaluation of XB, right evaluation of XB. What is the right evaluation? P4. So, you will get P4 here. And what is S3? It is the right evaluation of not recursively enumerable, right evaluation of XBA, right. Up to this you have read XB, then multiply by A. So, what is BA from the table? BA is C, that is XC. XC is P5, so this will be P5. Whatever you have, whatever value you have, you will write that. Each one of them will be either A, B or C, right. Is that clear? And what about R4? It is the right evaluation of XBB. What is the right what is the value of BB? BB is A. So, that the right evaluation of XA, and what is the right evaluation of XA here? P3. So, this will be P3. R4 is nothing but P3, right. And what about R5? It is the right evaluation of XBC. From the table, what is BC? BC is B. So, the right evaluation of XB, right evaluation of XB is P4. So, you will get P4 here. So, R1 is the left evaluation of XBL, which you have to determine. Then R2 is just P4, R3 is P5, R4 is P3, R5 is P4 from this. Similarly, for each state you have to write down the successor, A successor, B successor, you can write down all the mappings. And initially starting from Q naught, after reading A, to which state you will go? You will go to A, left evaluation is A, right evaluation is A, and the right evaluation or left AA, AB, AC, that is AAC, AAC, right. After reading a B, you will go to BB. What is BA? BB, BC, CAB, CA. After reading a C, you will go to CC, CA, CB, CC, that is BCA. So, from one phi tuple to another phi tuple, how we can go, that we have already seen, right. And what are the final states? The first and the second components are equal, same, those states are marked as final state. If the first component and the second component, if they are equal, those states are denoted as final state. In fact, these are all final state. This will be a final state, this will be a final state, this will be a final state. Okay. So, this is a deterministic diagram, and this will accept that particular set. Okay. Okay. This is not the only solution, you can give non-deterministic solutions also, there are other methods possible. So, it is not a sort of unique solution, it is one of the solution which gives you a deterministic machine, right. The second, actually this is the second portion of it, this is left evaluation. Value of x is the result when the symbols are of x are multiplied from left to right in the table as in the table, that is you are considering left evaluation only now. Now you are defining a language L1 set such that it accepts strings of the form xy where the string is of even length, xy should be of even length, and you divide it into half and the valuation of the first half is the same as the valuation of the second half. Okay. The second one is you have the same thing, but now they are not dividing them into equal halves, you are splitting the string and the first portion gives you value of x, second portion gives value of y if they are equal. You can split in any manner you want. So, the strings the L1 starting from the initial state you accept a string if this can be divided into equal portions such that the value of this is equal to the value of this. In the second one L2 you accept strings like this where the split can be, they need not be into equal portion, length of x need not be equal to length of y, you can split anywhere you want and the value of x should be equal to value. It should be possible to split it in such a way that the value of x is equal to value of y. X may be longer length, y may be longer, does not matter. How many of you were able to do this? Is L1 regular? Is L1 regular? Huh? No. Is L2 regular? Yes. L2 is regular, but L1 is not regular. L1 is not regular, L2 is regular. So, how do you show that? To show L2 is regular, you have to construct a finite state automata. For this, construct FSA. You construct a NFSA like this, K sigma delta Q naught F, where K has states like this, Q naught, then the symbols are A, B, no. So, you have A, B, C and also x, y, x, y, of course, sigma is ABC. Sigma is ABC. The states are initial state, then singleton states, 3 states, then pairs A, AB, AC, BA, BB, BC, CA, CB, CC, right. Now, Q naught is the initial state, F consists of AA, BB, CC. Now, we have to write the delta mappings. So, it is defined like this, delta of Q naught A, or I will write as Q naught x is equal to x. X can be A, B or C. X belongs to A, B, R, C, right. Then from this state, if you get a y, then y is also symbol, x is a state with this flower brackets. What will be this? There are two possibilities here. Either you go to x star y, right, or x comma y. This is a single state, this is pair, right. Now, if you have a pair x y and z coming, because x y z also belongs to sigma, what will be this? This will be x comma y star z. This is how the delta mapping is defined. In essence, supposing from Q naught, after reading a string, you go to a pair x y, you go to a state like this. That means it is possible to split it in such a way W1, W2 such that value of W1 is equal to x, value of W2 is equal to y. So, starting from Q naught, after reading a string W1, W2, if you go to x y, then it means that the string W is W1, W2, you are able to split it in such a manner, anywhere you can split, such that the first portion evaluates x, second portion evaluates to y. That is why these, if the left evaluation and the right evaluation are the same, you accept. From this, if I get a, to what state do I go? I go to x, y star a, right. So, this portion evaluates to x and W2a evaluates to y star a. So, you are justified in that writing this mapping. And what about this mapping? When you are after reading a string W from Q naught, if you are in a state W, the evaluation of left x, this would mean the evaluation of W, I will write it as x, where value of W is x. Now, after reading A, you can go to xa, that is the value of xa is this, that is again satisfied, or you can go to, there are two possibilities, it is non-deterministic, x comma a. Right, that is this WA you are able to split like this, the value of the first portion is x when you multiply, the second portion is a. Okay. So, you are justified in writing the mappings like that. Okay. So, this we have constructed this will accept exactly L2. So, L2 is regular. Now, we have to show that L1 is not regular. L1 is not regular. Usually to show something is not regular, what methods do you use? Pumping lemma or Michael-Nerod theorem and so on. We will use pumping lemma here. Consider this is not the only solution, you may give a slightly different solution. I will give one solution. A power 2n plus 1 CBA C power 2n. Look at this string. I have to divide into 2 halves, I have to divide it in the middle. What will be the value of a power 2n plus 1 c? What will be this? A will give you only A, AC will give you, let me have the table, what will AC? C. What is the value of BA C power 2n? BA is C, so this is C power 2n plus 1, BA is C, so you get C power 2n plus 1. What is CC? What is the value of CC? A. What is the value of CCC? That is AC, that is C. What is the value of C power 4? That is CA and CC, which is A, right. So, C power m equal to C if m is odd, C power m is equal to A if m is even. So, here you are having odd C, this is the same as value of this. So, this portion evaluates to C, this portion evaluates to C. What does that mean? This satisfies the condition given here. So, the argument has to start like this. Suppose L1 is regular, suppose L1 is regular, then A power 2n plus 1 CBA C power 2n belongs to L1 because it satisfies the condition. This is for any n. I have not taken any particular n, this is for any n, right, for all n, right. Then L1 has to satisfy the pumping lemma, L1 has to satisfy pumping lemma and let L be the constant of the pumping lemma. So, when you take this string, if you apply the pumping lemma, where will the pump occur? Pump occur within this, within the first n, first prefix of length n, the pump should occur, isn't it? So, pump will occur in A. So, suppose A power I is the pump, that is you can split this string in U, V, W, where V is of the form A power I, such that U, V power I, W belongs to L for all I greater than or equal to 0. I can be 0 also, such that U, V power I, W belongs to L. for all I greater than or equal to 0. This is the pumping lemma, right. Now, if you do that, a power 2n plus 1 minus I, take I is equal to the case when it is 0. So, I have used I whether I will say j, j, pump is a power j. So, this is j. Here also I have used I, here also I have used I, one of them can be different, just to make it not confusing. CBA, CBA, C power 2n should belong to L1, right. If j is odd, if j is odd, what do you get? The length of the string is odd. By our condition, the string has to be of even length, then only you can split it into 2 equal halves. So, you get an odd string belonging to L1, which is a contradiction. Odd length string belongs to L1 and that is a contradiction, right. If j is even, you have to consider both possibilities, right. J you can write as 2m, okay. If you write like this, what happens? You come to the conclusion a power 2n plus 1 minus 2m, right. CBA C power 2n should belong to L1, it should belong to L1, okay. We will show that this cannot happen, we have to show that this cannot happen. Odd, if j is odd, we have already seen, okay. Now, this you cannot do it in one step, you have to consider several possibilities. Suppose m is equal to 1, if m is equal to 1, what will be this? It will be a power 2n minus 1 CBA C power 2n, right. Then where will the split occur? Split occurs here. This string is of 2n plus 1, this is of 2n plus 1, okay. So, what will be the value of this? What will be the value of a 2n minus 1 CB? AC is, this will be a, then AC will be C, CB will be C. What will be the value of a C 2 power n? That is equal to value of what is AC? C, C power 2n minus 1, that is A. C power n is A if n is even, C power n is C if it is odd. So, they are not equal. So, m is 1, it does not work out. Then m is equal to 2, when n is equal to 2, this will be a 2 power n plus 1 minus 4, that is minus 3 CBA C power 2n. Where will the split occur? It will occur here. This is of length 2n, this is of length 2n. So, this will evaluate to A, and what will be the evaluation of this? This is A, AC is C, CB is C, CA is B. They are not the same. So, this also is ruled out. Then see the split, where if it occurs within this portion, you have to be careful. If the split is going to occur in the C, we have to consider separately. So, m, the rest of the cases m greater than 2. So, in that case the string is A 2 power n plus 1 minus 2m, C B A C power 2n, and this I can write as A power 2n minus 2m plus 1 C B A C power 2n minus 2m C power m 2m, or I can write it as A power 2n minus 2m A C B A C power 2m C power 2n minus 2m. So, this portion is length 2n minus 2m, this power is 2n minus 2m, this one I have to split into equal halves. So, this itself I can write as m minus 2 m plus C power m plus 2. So, what will happen? This is 4 plus m minus 2 is m plus 2. So, the split will occur here. What will be the length of this? 2n minus 2m plus m plus 2. This is 2n minus 2m plus m plus 2. Split will occur like this. Now, what will be the evaluation of this? Value of A power 2n minus 2m A C B A will evaluate to A, then AC is C, CB is B, BA is C, C power C m minus 2, C power this is A, then ACBA C power m minus 2. What is AC? C. What is CB? C. What is CA? B. What is BC? B. So, B C power m minus 1, B C minus m minus 3 and so on. Ultimately, it will become B, right. This will become B. And what about this portion? This is C 2n minus m plus 2. In a string of C's, depending on m is even or odd, this will be even or odd, the power will be even or odd. Either way, it is either it will evaluate to C or E. It will not evaluate to B. So, this is also not ruled out. So, whether J is odd or even, the pumping lemma shows that it is not regular. Okay. So, I will stop with this.